Okay, so what we have demonstrated here is a simple representation of the radioactive decay of a substance using a model of 6-sided die, each with one blackened side. So we toss them out randomly and remove all the die with the black side facing up, taking them to be the decayed particles, and we move them to our graph.
Bazinga!
So where does the exponential decay formula originate from? Well, scientists working with actual radioactive samples as opposed to our model here were able to empirically observe that the activity of a sample is directly proportional to the remaining amount of your sample n. So this can be expressed by dN by dt, which remember is the same as A. So dN by dt equals n times some unknown constant lambda, which is your decay constant. The negative is just conventionally included since you have a negative gradient. So basically you will end up with dN by dt equals negative lambda n. Of course, for our graph you may have noticed some anomalies to this observation, because it's just a simple representation of what's actually supposed to be happening. But in the actual experiment, with a proper radioactive sample, you're dealing with much larger numbers and the trend is much more reliable. So you should end up with that equation, dN by dt equals negative lambda n. So, on to the derivation of the exponential decay formula. So, you start with dN by dt equals negative lambda n. So this can be rewritten as 1 over n dN equals negative lambda dt. By integrating both sides, you can move on to ln n plus some constant equals negative lambda t plus some other constant. Of course, you can group these constants together to make some other unknown constant, which we'll label C3. So ln equals negative lambda t plus C3. So far, so good. Now we can then go on to say that n equals e to the negative lambda t plus C3. And of course, we can split up that exponent into n equals e to the negative lambda t times e to the C3. Now, of course, to get n naught into your equation, all you have to do is substitute t equals 0 into your existing equation. So, because of course when no time has passed, you're going to have your maximum amount of your radioactive sample, which is n naught. So, by substituting t equals 0 in, you get n equals e to the negative lambda 0, so that's 1 times e to the C3. So basically you just get n equals e to the C3. So basically that when time is 0, you know n has to equal n naught, so you know e to the C3 has to equal n naught. So your final equation will be n equals e to the negative lambda t times n naught, which is of course your exponential decay formula. So the final thing we want to demonstrate in this video is how you can find your decay constant lambda. So we are going to head back to our equation, n equals n naught e to the negative lambda t. And if you ln both sides of this equation, you actually get it into linear form. So you get ln n equals negative lambda t plus ln n naught. So this is, this is linear form. It's like equivalent to your y equals mx plus c. So you can plot a graph of ln n against t, and you'll get a graph with a straight line graph with a gradient of negative lambda and a y-intercept of ln n naught.